Hello, welcome to our sixth lecture, Synthesis of a Carbohydrate Phosphonate Analog via Pentacovalent Oxophosphorus Methodology. So before we dive into this phosphorus methodology, we need to first familiarize ourselves with some phosphorus functional group nomenclature. Here we have phosphates, which contain a hydrolyzable phosphorus-oxygen bond, and we have phosphonates, in which the phosphorus-oxygen bond is replaced with a non-hydrolyzable phosphorus-carbon bond. So an example using phosphates in nature is shown on this next slide. And it's the biosynthesis of KDO and its incorporation into the lipopolysaccharide that makes up the bacterial cell wall of all gram-negative bacteria. So arabinose is a sugar that gram-negative bacteria metabolize to form the KDO trimers, which form the lipopolysaccharide outer membrane. Here you start out with ribulose, and in the biological system, it's exposed to an isomerase to form the D-arabinose 5-phosphate. The enzyme KDO8-phosphate synthase then prepares the KDO8-phosphate. KDO8-phosphate phosphatase then forms KDO, and CMP-KDO synthase forms KMP-KDO. KDO transferase then links these together to form trimers, or lipophilic building blocks to build your lipopolysaccharide. So where this becomes of interest is you can see you have a cleavable phosphorus-oxygen bond, which I can show right here. And if we replace that bond with a non-hydrolyzable phosphorus-carbon bond, it's believed that this biological pathway can be inhibited. So how do we go about preparing the D-arabinose 2-phosphonyl-methyl target? Here is presented the retrosynthetic analysis. We can take the cyclic sugar structure and we can make it acyclic. Once it's acyclic, you can notice the aldol retron, and I will go ahead and circle that here. For those of you that are unfamiliar, that's basically your aldehyde with your alcohol, or your aldol retron. We can get that from the chiral aldehyde and the corresponding pentacovalent oxyphosphylene, which we get from this desired enone. We decided to use the acylsilane as the aldehyde synthon due to the low yields obtained when acrolein is used in the form the P5. So when we look at the forward synthesis of our acylsilane, we take propargyl alcohol and we react it with our allylic ether in PTSA to form the desired alkyne. Treatment with potassium tert butoxide forms the allene intermediate, which can further be synthesized to the acylsilane using N-butyl lithium at negative 85 degrees, followed by dimethyl phenylsilyl chloride, followed by an acid workup using sulfuric acid. So once in hand, we can do our electrophilic condensation of our pentacovalent phosphylene. We do this by taking our product and condensing it with triethyl phosphite to form our P5 complex. This chemistry was pioneered by Ramirez. The P5 can then undergo a phosphonyl with the chiral aldehyde and water workup to yield a mixture of products with a diastereoselectivity of 20:1. We take our major product and we can go ahead then and expose it to hydrogenation, followed by TMS bromide and methanol to yield our desired D-arabinose 2-phosphonyl-methyl derivative. By putting this derivative, which we now have the carbon-phosphorus bond, which is non-hydrolyzable, into the biological system, we believe we can inhibit the KDO pathway and therefore kill the bacteria.